Hello again. Let's go ahead and take a look at section 2.4, which is on complex numbers. Now, we're not going to do everything that's in this section. We used to, but we've cut some of the material out because it's becoming less important as time goes by. One of the things that we're not covering is higher powers of the imaginary number. And the imaginary number, of course, is I. So we're not going to cover what I to the 15 or I to the 32nd is. It is not a terribly difficult topic. If you want to read through the textbook, it is in there and you can learn how to do it. Basically, it repeats in a pattern every 4. So you have I, and then you have, well, let's see, what would we have? I, square root of a -1. And then I times I is I squared, which is a -1. And then I cubed is a negative I. And then I to the 4th is back to 1 again. So, and then it repeats. I, 1, no, I, -1, negative I, 1. The next thing that we're not going to cover is rationalizing the denominators. We used to always teach this as a form of division, but these days, computers and other electronic devices handle division by complex numbers just fine, and there's really no need for us to continue doing that. But again, it is in the textbook. If you want to learn how to do it, you can follow along there and see how it's done. So what are we going to learn? We're going to focus on what the definition of the imaginary number is and what it represents. And then we're going to talk about adding them, subtracting them, and multiplying them. Those are the main 3 things we're going to do. Add, subtract, multiply, and define what the imaginary number is. So let's get started. Let me share my screen with you very quickly. Okay, what I have here in the first problem is the square root of a -49. When we're looking at that, we want to be able to rewrite this in a different format. Square root of a -49. Well, first off, there is no number, no real number that we can take and multiply by itself and get a negative number. If you multiply a number by itself and it's a real number, well, 2 positives multiplied together give me a positive, and 2 negatives multiplied together give me a positive. The only way to get a negative number is to take an imaginary number. Now, what does that mean? We've basically set a definition. A definition is written with a 3-bar equals, and we call this I, the imaginary number. I is the imaginary number because it represents a way of dealing with those numbers whose squares give us negatives. What we're going to do is we're going to take our radicals, which are negative, and we're going to separate the negative from it as the square root of a -1 multiplied by the square root of another number. You can only split apart radicals between things that are multiplied together or divided. You cannot split radicals across things that are added or subtracted, and I'll show you why. So what we're going to do is we're going to rewrite the -49 as -1 times 49. This lets me split it into -1 times the square root of 49. The square root of a -1 by definition is I, and the square root of 49 is 7. Now, I is really a number, but we treat it sort of like a variable, but it's not. It is a number, but we'll put the 7 at the front. That will be the answer to this problem, 7i. Now, I said there's a reason you cannot split across addition. Let's test it on something we know and see if it's true. We're wanting to know, is this equal to the square root of 9 plus the square root of 4? Well, the square root of 9 is 3, and the square root of 4 is 2, which gives me a 5. On the left, though, 9 plus 4 gives me 13. 13 is less than 16. The square root of 16 is 4, so the square root of 13 is less than 4, 3 something. This tells you that these two are not equal. And you cannot split a radical across things that are added or subtracted. Multiplication and division, yes. Addition and subtraction, no. Let's take a look at the next problem. On the next problem, we have 3 times the square root of a negative 100. This is mostly a review of radical practice for you with the negative thrown in as a new topic. Again, we're going to take the negative 100 and we're going to rewrite this as the square root of a negative 1 times the square root of 100. The square root of 100 is 10, which gets multiplied by the 3. We basically have a 3 times I times 10, which will give us 30I as our answer. Let's take a look now at this next problem. It is very tempting for students to want to put the 16 and the negative 9 under the same radical and then say that the negative times the negative gives you a positive, so that it would end up being the square root of 144, which is 12. The problem is negatives can't cross the radical symbol. They can't go outside. So you cannot combine the two. The negative can't cross. So what we're left with is the following. Oops, this is number 3. The negative 16 and the square root of the negative 9 has to be split up as the square root of a negative 1 times the square root of 16 times the square root of negative 1 times the square root of 9. Now the 16 and the 9 can be combined together into the square root of 144. But you could also go ahead and reduce here, which would be simpler since they're smaller numbers. The first square root of a negative 1 gives you an I. The square root of 16 is 4. Square root of negative 1 is I again. And square root of 9 is 3. The 4 times 3 gives me a 12. And then I've got 2 i's, I times I, which gives me I squared. Now we have another definition. What is it that we get when we square an I? When we square I, remember that I itself is the square root of a negative 1. So when I square the I, I'm squaring the square root of a negative 1. And that means that it lifts off the radical and gives me the number that's underneath, which is negative 1. I squared then is equal to negative 1. This is something you'll want to memorize. Remember a minute ago, I said we weren't going to do higher powers, but I will go through the definitions for you, at least the first pattern. I is the square root of a negative 1. So I squared lifts off the radical and gives you the negative 1. I cubed can be thought of as I squared times I, which gives you a negative I. And I to the 4th means that you've got 4 of them. These two make a negative 1. These two make a negative 1. And negative 1 times negative 1 is a positive 1. And then it repeats again. So I to the 5th is I to the 6th is negative 1, I to the 7th is negative I, and I to the 8th is 1. It repeats every 4. Our answer up here then, since we have 12I squared, must be negative 12. Let's take a look at this next problem, which has multiple problems within it. We're going to write each of these out just to make sure that you really do have down what all the different values are. I believe this is number 4. We have 9 plus the square root of negative 64. You can do this more simply in your head if you want to, now that we have the definition down, by writing this as 9 plus the square root of 64 is 8, and the square root of negative 1 is I. Now, this gives us what's called a complex number, which consists of 2 parts and an I. It has a real part, which is the number that doesn't have I attached, plus the imaginary part, which is attached to I. So it has three parts. The real part, which is the number by itself, added or subtracted to the I part. The I part has a coefficient attached, and that number is called the imaginary part. And then it's multiplied by I. I, in other words, is not a part of the imaginary part. The imaginary part is just the coefficient. So in this case, the imaginary part is 8, and the real part is 9. This is what we call a complex number, which is sort of a combination of real numbers and imaginary numbers. They are real. They do exist in the real world. Imaginary just means not real, not that it doesn't exist. I know that's confusing, but I don't think they were thinking when they named it. Let's take a look at the next example, which is -9 times the square root of -64. Again, when we look at these, remember that the negative under the square root is going to give us an I, and the square root of 9 gives us 3. That gives us 3I times, because these were multiplied. The negative under the radical gives us an I, and the square root of 64 is 8. 8I. The 3 is the imaginary part here. The 8 is the imaginary part there. 3 times 8 gives me 24. And I times I is I squared. But we've memorized that I squared is -1. So this gives me -24. Basically, I squared changes the sign. That would be the answer to that part. What about the next one? 9 divided by -1 under the radical. Well, that would give me 9 over I. And that's a good way to write that one. Now, if you wanted to get it so that the denominator didn't have I in it, what you would do is you would multiply it by I divided by I, because I times I would give you I squared. And what is I squared? Oh yeah, it's a -1. So I have 9I, well, I should wait and do that step next, divided by -1. And then I can float the negative up and it becomes -9I. Right? Let's take a look now at the next one. The next one is the square root of -1 over the square root of -1 times the square root of -9. Remember, the negatives cannot go through those symbols. You must have an I for each time you get a negative under a radical. This is going to give me I in the numerator, I in the denominator, and another 3I in the denominator. Now, I divided by I does cancel. It is 1. And this leaves me with 1 over 3I. Again, if I don't like having the I in the denominator, I can multiply the top and the bottom by I over I, which is a form of 1. That will give me 3I squared in the denominator. I squared is a -1, which becomes -3 in the denominator. The negative is a floater. It could go out front or in the numerator. You could call this -1/3 times I. What about the last one? This last one has parentheses and some distribution. It works basically the same as it's been working. The rules in mathematics don't change because the type of number changes. We have -5 times 3 and -5 times the square root of a -64. The first thing I do is -5 times 3, which gives me -15. Then I have a -5 times the square root of -64. Notice the negatives do not become a positive because 1 is under a radical. That means it's I, not a negative. This gives me -15 plus, or I could write it as -5 times I, and the square root of 64 is an 8. So I have 5 times I times 8, which is a negative 40I. This gives me negative 15 minus 40I. This is written in complex number form. The real part goes first, negative 15, followed by the imaginary part, negative 40, multiplied by I. I is not part of the imaginary part. It's only the coefficient. Now let's switch gears and add them together. We want to talk about how to add complex numbers. If we're adding complex numbers, the rule is exactly what you think it would be. You're going to combine what look like terms. You're going to add the real parts together and add the imaginary parts together and keep the I. In other words, you're going to rearrange this so it looks like 1 minus 3I plus 3I. Well, 1 minus 1 is 0, and negative 3I plus 3I is also 0, and 0 plus 0 is, well, 0. Now, can you write it as a complex number? Well, you could write 0 plus 0I, and that would put it into complex number form. Or you can just write 0. I'm not sure what WebWork is looking for. Let's give it a shot. Let's just try 0 and see if it takes it. Yep, it liked it just fine. What about subtraction? Looking at problem number 6, we see that we've got subtraction. In number 6, we have 3 plus 5I minus negative 2 plus 10I. Well, if I didn't tell you they were complex numbers, what would you have done? I know, you distribute that negative, of course, so do it. And that gives us 3 plus 5I minus a negative 2 becomes plus 2, and minus a positive 10I becomes minus 10I. Always draw those arrows to prevent making a mistake. Then we have 2 real parts, 3 plus 2, which gives us 5, and 2 imaginary parts, 5 and negative 10, which combine to give us negative 5, with the I attached to indicate that that is the imaginary term in the complex number, 5 minus 5I. The next 2 problems are just like the previous 2 problems in that they're subtraction and addition. Again, combine the real part with the real part, the imaginary part with the imaginary part. If you need to distribute, be sure to distribute over both the real part and the imaginary part on the inside of the parentheses. Now let's talk about multiplication. The first kind of multiplication we want to look at is the one on number 9, where we basically have what looks to be a single term times 2 terms. And that's essentially what it is. We have a 3I, which is a factor here, multiplied by a combined factor term, 1 minus 4I. There are 2 terms in this parentheses, the 1 and the negative 4I, and only 1 term here. It does look a little weird with the 3I at the back, so if it bothers you, just move it around to the front. And then what do you think you're going to do? Of course, distributive property. So we're going to use the distributive property to distribute the 3I over both terms on the inside. 3 times 1 is 3 with the I still attached. 3 times negative 4 is negative 12, and I times I is I squared. But we know I squared is a negative 1, so it changes the sign of that term, and it becomes 3I plus 12, which is backwards to the way we normally write a complex number. So then we rewrite it as 12 plus 3I in the correct order. Real part plus or minus the imaginary part multiplied by I. The next problem is essentially just like the previous problem, where you'll distribute the I over both of the terms on the inside of the parentheses. The problem after that, however, is a little bit different. It is similar to a binomial multiplied by a binomial, and we can use the same FOIL process that we use in the United States to multiply them out. We have -1 minus I times 3 minus I. We can use FOIL, which stands for first multiplying the -1 times the 3 plus the outer, which is -1 times the -I, and the inner, which is the -I times the 3, and the last, which is -I times -I. Again, first stands for the first term in each binomial type object. That gives us -1 times 3, which is a -3. Outer stands for the ones on the outer edges of the expression. The -1 from the first set of parentheses multiplied by the -I from the second set of parentheses. That gives us plus I. Then the inner is the second term in the first parentheses multiplied by the first term in the second parentheses. And that will give us a -3I. The last term is the last term in each set of parentheses multiplied together. -I times -I is a positive I squared. Now we can combine the like terms of I minus 3I to get a -2I. And we can reinterpret I squared as a -1. That gives us two real parts, -3 minus 1, which becomes -4 minus 2I. Notice that the product of these two complex numbers is another complex number. Let's take a look at another problem similar to that one. Let's take a look at 13, which is a rather more difficult problem because it has radicals inside of it. We have the square root of 10 plus the square root of 13 times I, not under the radical, times the square root of 10 minus the square root of 13 times I, not under the radical. Do you notice that these are identical expressions except for the sign in the middle? That sounds a lot like the difference of two squares pattern, and it is the difference of two squares pattern. It's also called a conjugate pair. That means one has a plus sign and one has a minus sign. When you do these, what happens is the outer product and the inner product cancel and go away, and you're left with the first minus the last. We'll go ahead and use FOIL in order to prove that this occurs and that the outer and the inner products have the same value but opposite in sign, so they cancel. First, we get the first, which is, of course, square root of 10 times square root of 10. Then the outer, which is the first one from the first set of parentheses and the second one from the second set. Then we have the inner, which is the middle pair, square root of 13I and square root of 10. Then the last, and I'm running out of room, square root of 13I times negative square root of 13I. Now, the square root of 10 times the square root of 10 is the square root of 10 squared, which is 10, right? This is the square root of 10 squared, and the square lifts off the radical, and you just get what's underneath, which is 10. Notice that this second term becomes minus the square root of 10 square root of 13i, and the inner term is plus the square root of 10 square root of 13i. These are exactly the same, but opposite in sign, so they cancel to become 0. The last one, they are the same, but one's positive and one's negative. So we'll get a minus sign, accounting for the first minus the last. And then we have square root of 13 times square root of 13. And I times I gives us I squared. The square root of 13 squared is 13. And I squared is a -1, which will change that sign. And this then becomes 10 plus 13, which equals 23. It's true, the conjugate pair leads to not another complex number, but to a real number, which is just 23. So a conjugate pair where they're the same exact values in each set of parentheses, but with opposite signs in the middle, should lead to a real number. Let's take a look at one that won't happen that way. This is problem number 14. In problem number 14, you have -8 minus 12i quantity squared. Don't make the mistake of thinking this is a conjugate pair. It's not a conjugate pair. They're identical, sign included. They don't have opposite signs. They're the same. So we have -8 minus 12i times -8 minus 12i. This time, let's multiply it out and do parts of the FOIL in our head. So when we do the F for the first, we have -8 times a -8, which gives us 64. The outer gives us a -8 times a -12i, and the double negative gives us a positive 96i. On the inside, the -12i times the -8 gives us another 96i. Notice that this doubles. This always happens with something that looks like a binomial being squared. The middle term doesn't cancel, it doubles. Then the last gives us -12i times -12i. The double negative makes it a positive 144, and the I times I makes it I squared. But remember that I squared is a -1, so it changes the sign and becomes minus 144. The 96i plus 96i gives us 192i. Then we have two real terms or real parts, which is 64 minus 144. When we do that, we should get, well, what do we get? 144. 80? Is that what we're getting? Yep, 80. And it should be negative. So we get -80 plus 192i for our final answer for that one, for the complex number. The last problem on here, notice, has the pattern that we saw previously, the conjugate pair. 8 plus 5i times 8 minus 5i. Expect that this will become a real number without any imaginary part. This is the end of this video.